All right, welcome to chapter 3 of this chapter, or of this course. We're looking at atoms, and obviously you already know that atoms are the essential components that make up all matter, the simplest of components. There are subatomic particles, obviously, but the atoms are basically the building blocks of matter, as we'll see in this chapter. Okay, you can stop it here, the video, and just look through kind of the different sections and get a little preview of what we're going to be talking about. And then I would encourage you to answer these previous concept questions just to get you thinking about what you've learned in the past, and it's going to draw you into what you're going to look at in this chapter. Okay? So you go ahead and pause and take care of that if you haven't already. All right, section 3.1 of this chapter. Again, as mentioned, we're going to focus on the atom. And the first couple paragraphs here just kind of give you a historical perspective of how the idea of an atom was first kind of developed as maybe a certain material or a certain compound such as sugar. As that was crushed, it still retained the properties, doesn't matter how finely you crushed it. And so the idea was, well, there must be a minimal particle that is going to retain the properties of that particular compound. Okay? So can matter be divided into pieces forever, or is it made of miniature pieces that cannot be divided at all? That was the idea as scientists began to investigate this idea of how fine and how small can a particle or a compound be broken down into and still retain its properties, still be that compound, still be that particular material or substance. Okay? You can read a little bit here about the history and how this idea of the atom was originally devised and what the word means. Okay? So obviously some very big names here in the scientific community that first began to examine this idea of what an atom is. There are three basic laws that describe how matter behaves in chemical reactions, and we're going to investigate those three laws right now. Okay? First one is the law of conservation of mass. It basically says that you cannot create or destroy matter. I like to say we are not God, and as a result, we're not going to be able to create matter, nor can we destroy matter. All that can really happen is changes can occur. So you can have a chemical reaction or a physical change, but the individual atoms themselves have not been destroyed, nor have you created new ones. Law of conservation of mass. Another way to say that is when you have a reaction, a chemical reaction, the total mass before of all the reactants is going to equal the total mass after the reaction, the mass of all the products. So nothing is lost. The law of definite proportions. Let's look at this one. This one says a compound contains the same elements as a compound like H2O in exactly the same proportions regardless of sample size or source of the compound. So you could have an individual molecule of water, and the hydrogen and oxygen atoms are going to be in a ratio of 2 to 1, H2O. You could have a full glass, a gallon, a pool full of water, and the ratio of hydrogen atoms to oxygen atoms is still going to be 2 to 1 because that is the ratio in which that compound is formed. Okay? All right, and then law number 3 here says the law of multiple proportions. So this one is saying if you have two or more compounds, this is not a single compound, this is two or more compounds. So for example, you have H2O and you have H2O2, different compounds, and they're composed of the same two elements. So you'll notice we have water and hydrogen peroxide. They're different compounds, but they're both made up of hydrogen and oxygen. The ratio of the masses now, of the second element combined with a certain mass of the first element is a ratio of small whole numbers. Okay, and I'm going to show you this, an example of this in a little bit, and it'll make a little more sense. Okay, so law of conservation of mass, as I mentioned right there, you can read about that. We already kind of went over it. Law of definite proportions, you can read about it right here. And then let's spend a little time on the law of multiple proportions because it's the one that's a little more confusing. All right. So again, this is where you have multiple compounds that are both made from the same two elements. In this example, carbon and oxygen. So let's say we have carbon and oxygen, two elements, and they make up a compound. One possible compound would be carbon monoxide. The formula for that is just CO, one carbon and one oxygen. Okay? There's another compound that is made up of carbon and oxygen, but that is carbon dioxide, and its formula is CO2. All right? Let's say you have 1 gram of carbon for every 1.3 grams of oxygen in carbon monoxide. This is by mass now. This is not by number of atoms. Okay? Notice we have a 1-to-1 ratio as far as atoms, but oxygen is heavier. Oxygen is heavier than carbon. So it's a 1 gram of carbon for every 1.3 grams of oxygen, even though it's a 1 atom of carbon for every 1 atom of oxygen. Oxygen is heavier. In carbon dioxide, if you've got 1 gram of carbon, you're going to have 2.66 grams of oxygen. And so if we look at this, the ratio of the masses of the oxygen, obviously the ratio of the mass of the carbons is 1-to-1, but the ratio of the masses of the oxygen is going to be 1-to-2 because you have twice the mass of oxygen in CO2 because you have twice the number of atoms. That's all it's saying. So mathematically, you can just kind of see how that works out because any formula is going to have a whole number of atoms, and as you change the number of atoms, then the mass of that particular element is going to change by whole number quantities. The ratio between that is going to be a whole number. Okay? All right. Here's basically the idea that sustains the third law. Compounds contain atoms in whole number ratios. That's the idea. Okay? All right. Here's another idea that we need to make sure we understand. John Dalton, back in the 1800s, early 1800s, explained, again, a set of laws or a set of principles. And he reasoned that elements were composed of atoms and that only whole number of atoms can be combined to form compounds. His theory here is summarized in these 5 principles. 1, and you need to know these, all matter is composed of extremely small particles called atoms. Number 2, atoms of a given element are identical in size, mass, and other properties. That means every element, if you have an atom of carbon over here and an atom of carbon over here, they're going to be identical in size, mass, and other properties. All right? There is something called isotopes, and they have different number of neutrons, but we'll talk about that later on. But basically, they have identical size. Mass is, again, isotopes, we'll talk about that, and other properties. Now, atoms of different elements differ in these properties. So if you have carbon and oxygen, they obviously have different masses, different sizes, and different properties. Number 3, atoms cannot be subdivided, created, or destroyed. Now, that's not exactly true now. Again, remember, this was back in the 1800s. So, 2 and 3 are pretty much still true today, but there are some things that we're discovering that's a little bit different. Number 4, atoms of different elements combine in simple whole number ratios to form chemical compounds. So we mentioned that already. 8 hydrogen and oxygen combine to form water in a ratio here that is a ratio of whole numbers, 2-to-1. And in chemical reactions now, atoms are combined, separated, and rearranged. So that's the whole thing with a reaction. You're going to have things broken apart and then new things formed as a result of that reaction. Okay? These diagrams, you can study these diagrams. It's just showing you how you can visualize the theory here and the law of conservation of mass. So, you have a carbon and oxygen. You're going to have a carbon and oxygen afterwards, after the reaction. whether it is being decomposed or whether it is being formed. Okay? All right, reading check number 3, you can answer that. All right? And this is just talking about how Dalton's theory is going to support the laws we've talked about before, those 3 laws. All right, atoms. Let's talk about further within the atom. Let's subdivide it a little bit and talk about the smaller particles that are inside of the atom. Okay? So even though some of Dalton's ideas have been kind of revised, we don't throw it out all completely. Yes, all matter is composed of atoms, and atoms of any one element differ in properties from atoms of another element. That's still true today. Okay? So we don't completely throw out the atomic theory, Dalton's atomic theory altogether. It has been modified because of new discoveries and new observations. Okay? These are the 2 main ones here that have not changed over time. You can answer critical thinking number 4. And then you can answer the section 3.1 review questions here. And if you need help, I can help you. Or if you want to send it to me what your answers are, and then I'll send back the answers for you to check. Okay? Okay, in section 3.2 now, let's talk about the actual guts of the atom, what makes up the atom, the structure of the atom. Okay? So remember we were talking about John Dalton, and he mentioned that atoms are the basic building blocks. They are indivisible, which is not exactly true. We can look inside the atom and pull it apart into smaller particles. All right? But the atom is the smallest unit that retains the properties of a particular element. Okay? So the atom is now defined as the smallest particle of an element that retains the chemical properties of the element. There are smaller particles inside the atom, but you have to have all of those particles in the atom in order for the atom to still be a carbon atom or still be an oxygen atom and retain the properties for that particular element. So the nucleus, by the way, the particles we're going to be looking at are called sub, like under or within, deeper underneath the atom, okay, inside the atom here. The nucleus is the core of the atom, and inside that nucleus you have protons and neutrons. Okay? Protons and neutrons. And protons are going to be positively charged, and neutrons are going to be neutral in their charge. They have no positive and negative charge. And then somewhere around the nucleus, we'll talk about where those regions are, you're going to have these tiny, tiny, tiny little particles that are called electrons, and they have a negative charge on them. So atoms contain positive and negative particles. Again, positive ones are protons. They are in the nucleus. The electrons are residing outside the nucleus in the region, the cloud, they call it, the electron cloud around the nucleus, and they have a negative charge. So this here talks a little bit about how the electrons were discovered. You want to read a little bit about the cathode ray tubes, and basically the idea here is that a scientist took a tube here, and there's no air, no particles inside that tube, and devised it in a way, set it up in a way where there were 2 metal plates at either end, and then hooked that up to like a battery. And then that battery was providing a flow of current, a flow of electrical charges. And those electrical charges would pass through the empty chamber here from one side to the other side. The cathode here and the anode are the 2 sides of an electrical field, and as a result, those particles that were passing from one side to the other side, they were able to take that tube and put it into a magnetic field and see that that stream of particles actually was bending as a result of the magnetic field. And that's how it was determined what the charge is on those particular particles. And it was later decided that those particles were going to be called electrons. And those electrons have a negative charge, And it was also kind of in the same way that they were able to figure out what the mass of those electrons were. Okay, so you can read a little bit about this experiment here and understand how this particular cathode ray experiment helped scientists discover the electron that had a charge and even the mass of that. Okay, talks here about the charge and mass of the electron. So the idea here is the original model for an atom was this idea, this proposed model by Thomson, and he called it the plum pudding model, or maybe it was named after later on. But the plum pudding model basically is saying that there is a core, a nucleus, and inside that core you've got protons, and you've got your neutrons, and then outside of that core you've kind of got this big region here, this region where you're going to find the electrons. And those electrons are kind of just randomly placed around here in kind of what they call a plum pudding model. So this this soupy mess outside of the nucleus here is where all the electrons resided. Okay, so that was the original model, the original concept of what an atom looked like. It wasn't totally accurate, as we'll find out, but that was the idea. Now, here's another experiment that you need to be aware of, and the concept behind it helps scientists understand that a atom is mostly empty space. So the experiment was set up something like this. There is a very, very thin sheet of gold, extremely thin. Okay, this is your thin sheet of gold right here, and this source, this box right here, is providing a beam of very fast moving highly charged particles, radioactive particles. So that beam there was shot directly at this gold, thin gold piece of foil. Okay, and around this whole setup is this band of a material that is going to detect if it gets hit by a radioactive particle that are being shot from this box right here. Well, here's what they discovered. As these particles were being shot at the gold foil, what they expected is that the particles would bounce off the gold foil and ricochet in different directions, because they thought, well, gold foil is a pretty solid piece of metal, and as these particles hit the gold, they're going to basically bounce off and go in different directions. That's what they expected. What actually happened was most of the particles went straight through, and there's a big portion back here on this detective film back here. Most of the particles hit the detective film in the region behind the gold foil. Only once in a while was there a particle that ricocheted and bounced off and back in a different direction. But most of them, large majority, went straight through, and they were detected back here behind the gold foil. So, what did they determine from that? Well, you can read about it right here. What the idea is then is that this atom, if this is a single atom, the atom is mostly empty space. As that beam of alpha particles came whizzing through the gold foil, most of them went straight through, because the atom is mostly empty space. Only once in a while, if a particle came here and hit the dense nucleus, did it then ricochet off in a different direction. So this was astounding. Matter, even though it seems to be very solid, it actually is mostly empty space. That's pretty remarkable. Okay? So he discovered that the volume of the nucleus was very small, it's very dense, compared to the total volume of the atom. And the atom is huge compared to the size of the nucleus, meaning the atom is the distance from the size of the atom is from the nucleus all the way out to the farthest regions where there are electrons. Okay? So that discovery, you need to understand that, understand the experiment, and understand the implications of that and what was concluded as a result. Okay? As mentioned already, the nucleus contains your protons and neutrons. Okay? A proton has a positive charge, and it is equal in magnitude to the negative charge of an electron. So the electron has a negative charge, the proton has a positive charge, and they cancel each other out. One electron, one proton will cancel each other out. Okay? A neutron has no charge whatsoever, and is basically electrically neutral. Okay? There's only one atom that doesn't have both proton and neutron in its nucleus, and that would be hydrogen. So hydrogen, its nucleus just has one proton, has no neutrons in it. Okay, there are isotopes of hydrogen that do, but a hydrogen atom is going to have basically a nucleus with a single proton in it. Okay, and a single electron moving around it. You can read here about the proton, the mass of the proton. You don't need to memorize that. And the mass of the electron, which is tiny, tiny, tiny. Okay, so most of the mass of an atom is due to the proton and the neutron, which are both given an atomic mass unit of 1. All right, this mass here is measurement in actually kilograms, which you can see how tiny it is. 10 to the negative 27, 10 to the negative 27. Okay? Okay, every element is unique, and it is unique and it is determined by the number of protons that are in the nucleus. Okay? So, the number of protons determines the atom's identity. Every proton of an atom has for every proton an atom has in its nucleus, the same number of electrons surrounds the nucleus for a neutral atom. Okay? But you have to know that hydrogen is hydrogen because it has one proton. If you had 2 protons, it wouldn't be hydrogen anymore. It would be helium. A helium has 2 protons. Okay? If it has 3, it would be some different element. So the number of protons is what determines what the particular identification of that element is. Okay? Alright, so you can read and answer this reading check here. And this is just a summary of all the subatomic particles. The electron, the proton, the neutron. Again, you don't need to know these masses. You don't need to memorize them. You should know the mass number. You should know their charge. And you should know the symbols that are used to identify those different subatomic particles. Okay. It's very interesting that inside of your nucleus, let's say this is your nucleus here, you've got protons, you've got neutrons too, but those protons are all positive charges, and it is a common understanding that like charges repel each other. Positive and negative charges are attracted to each other, but all positive charges actually repel each other. So how is it that in a nucleus all these positive protons can actually stay in the nucleus and not just explode and try to get away from each other? It's amazing. So how do all the protons that have the same electric charge, how are they not repelling each other inside that nucleus? Okay? There is a force that exists. Again, we don't understand it. We don't know why it's there. But there's a force that exists between 2 protons that overcomes the electrical force trying to push them apart. Positive and non-positive push each other apart. But there's a different force that is holding them together if they're very, very close. So the force only acts when 2 protons are very close to each other, as they would be in a very dense nucleus. So that force is called the nuclear force, and it is one of the strongest forces in the universe. A similar force acts when 2 neutrons are very close together, or when a neutron and a proton are very close together. So there is a short range proton to proton, neutron to neutron, and proton to neutron force inside the nucleus that is keeping it all together. and that is called the nuclear force. As you get more and more and more and more protons inside the nucleus, that force has a harder time keeping all the protons in the nucleus. So when you get upwards of like 83 protons, then the nucleus becomes somewhat unstable and you have what is called a radioactive material. Okay, radioactive nucleus. It starts, pew, pew, pew. It's not able to hold on to all those protons and neutrons and starts shooting them out in radioactive, as radioactive particles. The radius of an atom is expressed in a very small unit called picometers. All right, 1 picometer is 10 to the negative 12 meters. Tiny, 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 tiny. The atomic radii are so small, very, very small. Okay, or the other thing here is that the mass of atoms and the subatomic particles. Notice kilograms here. It's so tiny that we use a unit called the unified atomic mass unit, where one of these is equal to that quantity of kilograms. Okay? The idea here is just that atoms are tiny and the subatomic particles are even more tiny. Okay? Tinier. So that's the idea there. All right, take a moment and see if you can't calculate this here. It says verify the value of the density of an atomic nucleus given above for a spherical atom with a mass of 1 unit. Recall the volume of a sphere is this. So mass is, density. We want the density. Density is mass over volume. So you're going to take this mass right here. It's talking a spherical atom with a mass of 1 U. That would be this here. That value over the volume that you're going to calculate. Okay? And the volume here take these values up here. So you're just basically going to take the mass over the volume, and you can express it in kilograms per meter cubed or kilograms per centimeters cubed, but this is the radius, so this radius is going in to that formula. Notice it's radius cubed. Okay? Alright, that concludes 3.2, so go ahead and spend some time answering these questions and let me know if you've got any problems with these, and I'm happy to send you the answers when you're done working through those. Okay? Alright, the last section in chapter 3, we're going to be talking about atoms again, but we're going to be talking about a quantity that is used in order to talk about how we count atoms. Atoms are so tiny, we don't usually say 1 atom or 2 atoms or 3 atoms, right? So we talk about large quantities of atom, and we package them together in a quantity that is called a mole. And we'll talk about that today, okay? Alright. So the idea here is that in most experiments, or most cases where we're talking about atoms of a particular substance, atoms are so small and so numerous that we don't talk about single atoms. Okay? So we usually make calculations that take into account the properties of large groups of atoms. Again, that large group is going to be something called, it's just a quantity, okay, but it's going to be called a mole, So all atoms of an element must have the same number of protons but not neutrons. Oh, we already mentioned that, okay, just highlighting that again. An element is identified by the number of protons. It can have different number of neutrons, and that would be called an isotope, but every hydrogen atom has 1 proton. Every helium atom has 2 protons, and so on. Every lithium atom has 3 protons. It can have different number of neutrons. Those are called isotopes. They can even have different number of electrons compared to other elements of the same elements. Those are called ions, but they have to have a certain number of protons in order to be that particular element. Okay? That is also called the atomic number. So hydrogen's atomic number is 1 because it has 1 proton. Helium's atomic number is 2 because it has 2 protons in its nucleus. Lithium's atomic number is 3 because it has 3 protons in its nucleus. Okay? So when we look at the periodic table and we look at a particular element, you'll see there is a symbol for that element. In this case, this is for lithium. There's an atomic number which tells us the number of protons. There is an average mass. That's not, this number right here is not the mass of one particular lithium atom. It's an average because there are some lithium atoms that have 3 protons, as they all would, and it might have 3 neutrons. But another lithium atom might have 3 protons, which it has to have, but it might have 4 neutrons. The number of neutrons can be different. Those are called isotopes. All lithium atoms have 3 protons, but they might have varying number of neutrons. You'll notice that this is close to 6, this is close to 7. Every proton has a unit mass of 1, every neutron has a unit mass of 1, so this particular isotope has a total unit mass of 7, whereas this one has a total unit mass of 6. And it is the average of the two that's going to give you this mass here. That means there must be a lot more of this lithium in the world. So a sample of lithium is going to have a lot more of this isotope where there are 4 neutrons than it would this other isotope, because the average, the weighted average, is very much closer to 7 than it is to 6. Okay? And that's what this is talking about here. All right? So you can read a little bit about that and answer these questions here. So the isotopes are all going to have the same number of protons but different number of neutrons. Here are 3 isotopes of hydrogen. So they have names: protium, or sometimes called hydrogen 1. Actually, that would just be hydrogen, maybe hydrogen 0. I don't know, because it has 0 neutrons. This has 1 neutron and 1 proton. This is 2 neutrons. So notice this has a total mass of 1. This has a total mass of 2, because the neutron and proton both have a unit mass of atomic unit mass of 1. And this has 3 neutrons and 1 proton, so this has 3. And you'll notice when you look at hydrogen, the total average mass of hydrogen, of all the hydrogen in the world, is going to be the average, the weighted average of these 3 isotopes. Okay? Okay. This is a table that shows this, the mass number of hydrogen isotopes. So you've got your 3 different hydrogen isotopes. They all are going to have 1 proton, but they're going to have varying number of neutrons. Okay? So this would have a total mass of 2, or 1, this would have a total mass of 2, and this would have a total mass of 3. Okay? So the way that you might write those different isotopes would be this. You use the symbol for the element, and then as a superscript you put the mass, and as a subscript you put the atomic number. Okay, so H21, H11, something like that. Okay, so the nuclide here is a general term for the specific isotope of an element. So you have 3 different nuclides. Okay, it's just showing you what's in the nucleus of those particular isotopes. So answer 4 and 5 here, and we'll come down and we'll talk about this table. So it's showing you different isotopes. Here are 3 isotopes of hydrogen. Here are 2 different isotopes of helium. Here's how you can write the symbol for those different nuclides, showing you the number of protons and neutrons. Protons and neutrons, the mass. Okay, the top number here is going to be the total number of protons and neutrons. The bottom number is going to be the total number of protons. Because the top number is the total mass, which is protons and neutrons, and the bottom number is the number of protons, the atomic number. So here, if you've got 1 and 1, that means you've got 1 proton and 0 neutrons, and the number of electrons in the neutral atom is always going to be the same as the number of protons. It's not written here in the symbol, it's just understood. Here, if you've got hydrogen 2, you've got 2 and 1. So if you've got 2 and 1, that means 2 is the mass, which must mean you've got 1 proton, because you always have 1 proton of hydrogen, and you must have 1 neutron then. If you've got hydrogen 3, well, you always have 1 proton, and you must have 2 neutrons to make a total mass of 3, and you're always going to have the same number of electrons as the number of protons in a neutral atom. Helium, if you've got helium 3, notice it's helium 3 here, this is going to be helium 3 because the mass is 3, and the number of protons is 2, that's the atomic number, so you got 2 protons, same number of electrons, you must have 1 neutron in order to give it a total mass of 3. And helium 4, you've got 2 protons always for helium, same number of electrons, you must have also 2 neutrons to give you a total mass of 4. Okay? Alright, walk through this sample problem and see if you can understand how many protons, electrons, and neutrons there are in chlorine 37. Again, chlorine 37 is telling you the mass, and then for chlorine, you'd have to look up the atomic number and know how many protons, and then the difference would give you the number of neutrons. Okay? Try this practice A as well. Okay, atomic mass is a relative measure. Here's all that means. It is compared to something else. The atomic mass for all the elements, all of the atomic masses are compared to a single mass of a particular element, and that would be for carbon 12. So carbon 12, a unified mass unit, is defined as 1/12 of the mass of carbon 12. Okay? So all this is saying is that all the masses on the periodic table are all compared to carbon. Okay? That's what it's saying. Okay, let's just walk through this quickly. Here are 2 isotopes of hydrogen, showing you the mass number and what percent of all the hydrogen is made up of those particular isotopes. Okay, so this right here, this number is the average atomic mass of hydrogen. Well, you notice how close it is to 1. That must mean there must be very little hydrogen 2 in the world and hardly any at all hydrogen 3, because you can see 99.9% of all the hydrogen in the world is hydrogen 1, and that means that when you take the weighted mass of this, you would take 99.9% times this number plus 0.011% times this number, and you're going to get that weighted average right there. Okay? So you can see that by looking at the average here, the average, since it's closer to this first one, that's telling you that most of the hydrogen in the world is hydrogen 1. Same with all these others as well. All of these weighted averages, these weighted masses, those are not the masses of individual atoms. It is the average. So it's going to have, decimal values here. Whereas you'll notice the masses over here are 12 and 13, 16, 17, 18, 63, 65, 131. Well, when you take the weighted average, when you take 98.93 times 12 plus 1.07, actually I should change those percentages, times 13, you're going to get that number. So you can see how close it is to 12. That's because the majority of all the carbon in the world is carbon 12. Okay? And that's what this talks about right here. And there's an example. You can look through this example and see how they're calculating the average atomic mass, the weighted average of, I think they use 3 different isotopes here for copper. Copper 63, copper 65, and oh, I guess it's just 63 and 65. Yep. So 63 and 65. Okay? All right, you can answer these questions here. All right, let's talk about a very important concept that you must understand because we are going to use it for the remainder of the course. You have to understand this because it will come up again and again and again and again and again. All right? All right, as mentioned before, large quantities of atoms or compounds or molecules are used. We don't usually talk about individual molecules or individual atoms. That quantity that we use in chemistry, that large quantity, is called a mole. So by definition, the idea is simply this. That we'll look at the definition in a second, okay? But here's the idea. If you have a particular volume here, and we'll learn about this later on when we talk about gases, and the particular pressure on this container, the pressure is fixed, and the temperature of the gases inside there are set, all right, for a particular volume and a particular temperature and a particular pressure. The number of particles, if we get this just right, the number of particles inside this container of a gas would be a very, very large number. And if we get the pressure and the temperature and the volume just right, we would have a mole of particles in there. Okay? And if we put a different gas in there and it has the same pressure, same temperature, and same volume, you would have the same number of particles in there. Okay? So the idea here is we'd like to use a quantity that is very useful in chemistry instead of talking about individual molecules or atoms. It's sort of like this. If you go to the donut shop and you order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 donuts, you have just purchased a dozen. Okay? So we talk about a dozen. I'll take a dozen chocolate. I'll take a dozen with sprinkles on it. I'll take a dozen whatever. Well, instead of saying 12 all the time, you say a dozen. In chemistry, instead of saying a large quantity, we say a mole. Now that large quantity has a specific value. Just like a dozen is 12, that large quantity is the specific value. Okay, we are talking about the mole here, and by definition, here's the definition of a mole. So a mole is the amount. Remember, mole is just, it's a number. I'll tell you what that number is in just a second. The mole is the amount of a substance that contains the number of particles that there are atoms in exactly 12 grams of carbon-12. So remember, everything is related to carbon-12. So if you have 12 grams of this element, you're going to have exactly a mole of particles. That number, remember, a mole is just a number. Just like a dozen is 12, a mole is this number. You ready? 6.023 times 10 to the 23rd. It is an astronomical number. It is absolutely gargantuan. That is 6 and then followed by 23, well, it's 6 and then 023 divided or followed by 20 zeros. That's how big the number is. It's huge. And that is how many carbon atoms would be in 12 grams of carbon. It's just, it shows you how tiny the atoms are. Okay? So, just remember that a mole is nothing more than a number. And here's how it's defined. Right there. You can read that and define that. Okay? So, if you have 2 moles of atoms, you're going to have 2 times 6.023 times 10 to the 23rd. If you've got 3 moles, you're going to have 3 times that number. If you have half a mole, you have half of that number. If you have a quarter of a mole, you're going to have a quarter of that number. So it's just a number to help us count how many particles we have. Okay? It's also called Avogadro's number because it's named after the scientist that discovered this. So he determined that 12 grams of carbon-12 would contain this many atoms. Okay, here they have 6.022. Okay, fine. All right. So 1 mole of anything. If you say I have a mole of cups, then you've got that many cups. If you have a mole of pencils, you've got that many pencils. It's just a number. Okay? Answer these 2 questions right there, and let's talk about molar mass. Now, here's what you should realize. We're going to talk about mass, and it's not just the mass of anything, it is the mass of a mole. So that's what this means. Molar mass means the mass of 1 mole of a particular substance. So if you had 6.022 times 10 to the 23rd atoms of carbon, then you would find out what the mass is of that. And it happens to be that, let's say it's carbon 12, well, the mass of that is 12 grams. Okay? But 6.022 times 10 to the 23rd atoms of oxygen. Let's say oxygen has a different mass. They're bigger particles. They have more protons and more neutrons, so it's going to have a different mass. Same number of particles, but the mass may be 16 grams. But it's still a mole. It's still a mole of particles. So the molar mass is different and unique for each particular element in each particular compound. Okay? So the molar mass of iron is a different value. It's a certain number of grams per mole. The molar mass of copper, 6.022 times 10 to the 23rd atoms of copper, are going to have a mass of 63.55 grams per mole. Okay? You're going to have to be familiar with molar mass because we want to be able to convert from mass to moles and moles back to mass. So the gram-mole conversion is going to help us go from mass of something to how many moles you have, or from moles back to mass. So mass is grams, and moles we're talking about a quantity. We're talking about how many. It's a number. Okay? So if you had, for example, you wanted to find the mass of 2 moles of a substance, then you would take 2 times the molar mass of that particular substance, because the molar mass is the mass for 1 mole. So if you want to find the mass for 2, you would double the molar mass. Or if you want to find the mass of a half a mole, you would take a half of the accepted molar mass of that substance. Okay? This little diagram is kind of showing you exactly how we do that. So if you're given the mass, let's say you're given the mass of something. You have 500 grams of something. You've got 200 grams of something. And you want to know, well, how many moles is that? And then you also want to know how many atoms would that be? Well, if you have mass and you want to go to moles, then you would actually, right here, you're going to take and divide by the molar mass. So let's just look at a quick example. Let's say you had 120 grams of carbon. How many moles is that? Well, you would divide by 12 grams because it's 1 mole per 12 grams. I know that I'm going to divide by 12 because I want the units of grams to cancel. So 120 divided by 12 is going to give me 10 moles. Let's say then I want to say, well, how many actual particles is that? Well, I know that in 1 mole, I have 6.022 times 10 to the 23rd atoms. So then I would multiply by Avogadro's number to get the number of atoms. If you want to go the other direction, if you know the number of atoms, you would do the inverse operations. So you would divide by Avogadro's number, and then you would multiply by the molar mass. Okay? So take some time right here and look through this sample problem. It's giving you mass, and it's asking you how many moles. So you're given the mass of aluminum, and you want to find out how many moles. And right here, you're given the mass per mole of aluminum particles. So follow this example here, see if it makes sense, and realize how they get this answer here. And then try this practice problem right there. And if you need help, I can help you. I can also send you the answer to that if you want to see. Try this sample problem. It says how many moles, and this time it says it's giving you the actual number of atoms. So you know that 6.022 times 10 to the 23rd is 1 mole. Well, you don't have 6.022 times 10 to the 23rd. So you got to figure out how many moles is this if 6.022 times 10 to the 23rd is 1 mole. Look through this example here, and then try C. Here you're given the mass, and you're asked to find the actual number of atoms. So this time you're going to go all the way from mass to moles, and then moles to number of atoms. You always have to go through moles. So mass all the way to atoms, there's not a step there. You've got to go to moles and then to number of atoms. Likewise, if you know the number of atoms, you've got to go back to moles and then to mass. Everything goes through moles by using the molar mass or Avogadro's number. Okay? So look through this example, try this practice problem here, and then you can answer the 3.3 review questions and walk through all of those, and you can double check. I'm happy to send you the answers so you can look at that. Okay? And then also take some time and look at the Chapter 3 review questions. So here are the Chapter 3 review questions. You'll notice it talks about Dalton's atomic theory and so on. You're going to want to know these different laws and understand what they mean and how to apply them and make some simple calculations with them. You're going to want to know about isotopes, and you definitely want to know about the mass of moles. Now, I just want to make a comment here. And number 8, I want you to notice something. 1 mole, 1 mole, 1 molar mass. That means the mass of 1 mole. 1 molar mass, the mass of 1 mole. 6.022 times 10 to the 23rd. That's a mole. This is a mole. All of these are saying 1 mole. 1 mole. In just different ways. 1 mole, 1 mole. What is the mass of 1 mole? What is the mass of 1 mole? What is the mass of that many particles, that many atoms? All of those are saying what is the molar mass. That's what they're all saying. What is the mass of 1 mole? Okay? So try all of these and see how you do, and then let me know if you have any questions. Okay? All right. Keep up the good work, and I'm here for you.